Hey guys, I guess it's Friday. No, that's no good. Hey guys, welcome to Friday. I thought about doing like a formal Friday, wearing a tie and a jacket, but still my pajama pants, which I'm always wearing. So we're ready to do these last three problems. I had a few questions about what to do in each case of a neutralization reaction, which is exactly the kind of questions I wanted these last six questions to trigger. So I'm going to do a little additional video probably maybe later today. That's going to have just kind of a quick outline of how you know which type of problem it is and what to do in each case. So I'll get you that in a nice summarized video. Again, if you're missing any pages of the worksheet, I sent you an announcement. I think it's called something like e-learning. It's what all the kids are doing or something like that on Canvas, and you should be able to get that. You should be able to get a copy of that. And even if you just have the digital copy, you could just write it out on a piece of paper, or just write number 29 or whatever. Also, thank you for the people that sent in corrections on number 28 yesterday. I think we got that squared away. I tried to put corrections on Canvas or on YouTube, but apparently on a school account or in a school device, you can't see any comments. So from now on, those corrections, like I said, will be coming through Canvas. All right, let's look at number 29. So I've done this thing again. Looks like I see a half a liter and a half a liter, so I'm going to end up with a liter. So I'm starting to think maybe that's not a good idea because it makes us forget about the volume on the problems when it's not a liter. When I say us, I mean me. But anyway, so I've got HCl. So HCl, of course, is strong. That's an old friend. And I've got this guy. So this is going to be a weak base, and I know that's a weak base simply because I'm reacting it in a neutralization reaction with a strong acid, but also because it's got a Kb, and I can see it's got a very small Kb, so it's a very weak base. So the first thing we want to do, as always, is put in our Chewbacca, and we need to have, of course, moles here. And so I've got half a liter of 0.0424 molar, so half a mole basically of my hydronium. And so some of you may be wondering why sometimes I write hydronium and sometimes I write hydroxide and sometimes I write, the guy. Like in this case, I'm writing the whole compound here. The reason is I only do this with the hydronium or the hydroxide with strong acids and bases because they completely dissociate. Anything else should not be written like that. Anything else, you should write the whole compound down. So strong acids and bases, you could just put the hydroxide or the hydronium because they're completely dissociated. Also with the hydroxide, sometimes there's two of them, so you have to make sure you're taking that into consideration. So it's nice to think of it as just the hydroxide and not the whole compound. All right, so with this, I'm going to have, since it's a half a liter of this molarity, the number of moles is going to be 0.0212. Once again, I've chosen easy numbers for you to do this with. Oh, I've got the same thing here. So these are in equal amounts. So this is a neutralization reaction, which means, so if I've got a neutralization reaction with a weak acid or base, I have to worry about that conjugate. If it was a strong acid and base and they were in equal amounts, they would completely cancel out. The conjugates are so weak that it doesn't do anything. They don't do anything. So the pH is going to be 7. But if I've got a strong and a weak in equal amounts, right, then the conjugate of the weak has some strength to it, right? So in this case, I've got a base that's going to have a conjugate acid, and I might not know what this acid is going to be, but so I can just write this. I can just put an H in front of whatever it is, H5N. There we go. That's the conjugate acid, and because it doesn't have a charge and it picked up a proton, now it's got a positive charge. So let's look at the changes. Minus 0.0212 because it's going to be neutralized by this. Minus 0.0212, it's also neutralized, but this, right, is still going to gain 0.0212, and because it's a conjugate acid of a weak base, it is going to make the pH slightly acidic. So we're going to have to look at that guy. here in a minute. We'll have to make an ice table and everything. So let's get to that. This is going to be 0, this is going to be 0, and this, of course, is going to be 0.0212. All right, so that amount of acid, of this weak acid, is something we have to consider. So I've made myself a little more room here. But this is what I got from that Chewbacca table. And that's the concentration because we did end up with 1 liter. So it was that many moles, but it's that many moles in 1 liter. So that's also the concentration. So that's our molarity. So using this, we have to make an ice table. So I'm going to have this guy. I'm going to have HC5H5N. And that's going to make our hydronium. And that's the thing that was going to tell us our pH. But it's going to make that after dissociating from this guy, which was the C. Oh, sorry, this is a plus on it. This is H5, and this is N, and that's our base again. But we don't have Ka, and we're going to need that, so we'll come back to that. Let's do our ice table first. So I've got this 0.0212. I've got none of this and none of this. That's my initial. My change is going to be minus X, and I'm going to get plus X because I'm only getting 1 hydrogen from that, so no 2s or anything like that to worry about. This is also plus X. So our hydronium ion concentration is going to be equal to X. And that'll be what we use to find the pH. And so we've got X for both of those values. And of course, this is going to be 0.0212 minus X. I'm not entirely sure that my Ka is small enough that I can ignore the minus X on that 0.0212. But let's take a look. So we need to turn this Kb into Ka. And so Kw equals Ka times Kb. So we can do Ka equals Kw over Kb, just dividing both sides by Kb, and that's going to be 1 times 10 to the negative 14th. That's Kw divided by 1.7 times 10 to the negative 9th. So that's my Kb of the conjugate base of this acid that I want to find, right? So that's the Kb of this base. This is its conjugate acid. And remember, these guys, these A and B, this and this have to be conjugates for this to be true. So we punch that into the calculator. We're going to find that Ka is equal to 5.88235 blah, 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 times 10 to the negative 6th. So that's plenty small. So that's small enough that we can definitely get rid of that X, which, you pretty much knew it was going to be. So that means that our Ka is going to be equal to X squared. I'm just taking this X times that X, right? Products over the reactants. But I'm just going to use 0.0212. So because I can get rid of that X because it's going to be a lot smaller because this value is so small. And so, of course, the Ka is equal to that thing we just did over there, 5.88. let's just say 235 times 10 to the negative 6th. Right, so you're going to solve for X. X in this case, you're going to multiply both sides by 0.0212, take the square root of both sides, and that will get us 3.5314 times 10 to the negative 4th. So it's not very much, but that's not surprising. We didn't expect it to be a big value. This is a very weak, it's a conjugate of a weak base in the first place. So that's our concentration of the hydronium ions, because that's what X is. That's what X is here, right? Our hydronium ions. So using this, we can find the pH, and it's just the negative log of 3.5314 times 10 to the negative 4th. And so that's going to equal, all right, let me write on here, pH, just so all the words are there. And the pH is going to be equal to, how many sig figs? Looks like I've got 3 on all my data, so 3.45 is my pH. All right, moving on to number 30. I've got a liter of some HBr. HBr that's strong. And blah, 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 of methylamine. So that's not one of my strong bases. So that, and it says a weak base. Plus it's got a Kb here. So yeah, that's a weak base. So I got a strong acid, I got a weak base. Now we need to know which one's in excess. And the best way to do that is with the Chewbacca. So put my Chewy table in here. 1 liter, that makes this easy. So this is 0.00211 moles. Remember, this is moles. It's right in a minute. And then I've got 1 liter of this also. So that's 0.00100 moles of, so this is the methylamine CH3NH2. Interesting. HBr. So this is the hydronium because it's a strong acid. So it looks like we're in excess of, the acid is in excess. So we're just going to lose, we're going to neutralize this much of it using this base. Now I could put the conjugate on here, but it's not necessary. I've got excess acid. I don't need the conjugate. I'm not going to do anything with any weak acids or bases. So this is just going to be simply find the pH from the concentration of the hydronium that's left. So this should be pretty easy. This is 0.00111, and this is 0. And there would be, there would be of the conjugate acid of that base right there would be 0.001. But that, again, it's going to be so weak compared to this strong acid here. It's negligible. It's not going to make any difference at all. I've got this, so all I have to do is find the pH. First, I need to check my volume because remember, these are moles. I've got 1 liter, so this is in 2 liters. So I have to divide this by 2 to find the concentration. So this is moles per liter. And that actually gets me 5.55 times 10 to the negative fourth. So 0.000555. So I just got to do the negative log of 0.000555. That's fun. And that should get you 3.2 sig figs, 3.26. And that's our answer for that one. Not too bad. You got to like it when there's excess strong because it makes the math easy. It makes it so that you don't have to do anything too fancy. All right, looking at number 31. I've got lactic acid. Doesn't even show a molecular formula. I added these decimal points on here so that we could have 3 sig figs. So I've got lactic acid. That's a weak acid. I know that because it's not one of the 7 strong ones that we should have memorized. I got barium hydroxide. That's a strong base. Remember, bases with big, especially the ones with the big group 1 or group 2, in this case group 2. And we got to remember to watch out for that 2 right there. That's going to be a factor. So let's dive right in and find out which there's more of. I've got 0.0068 moles of the, I'll just put lactic here. That works for me. And this is going to be the hydroxide, again, because it's strong. And that also makes sure that I account for that fact that there's 2 there. So I've got 500 mils, so half of that's going to be 0.00344. And this is going to be another half a liter, so I'm cutting that in half. But then I'm also doubling it, so it's just going to be 0.00120, right, moles of the hydroxide ion. Doubling it there, half a liter there, so 2 times a half. So it looks like I've got more of the lactic acid. So with the lactic acid in excess, we're going to lose this hydroxide. That's going to go away, and we're going to neutralize the same amount of the lactic acid. And that's going to make this 0. It's going to make this 0.00224. And in this case, because I've got excess lactic acid, I've just neutralized some of this. I made a buffer, so I need this lactate here. And if you don't know what the lactate should be, you could just put in, this is the conjugate. If you didn't know that lactate is the conjugate base of lactic acid, that's fine. Just put the conjugate. You can write conjugate or just CONJ, something like that, so that you know that you're looking at the conjugate. And so in this case, it's going to be 0 to start with. It's going to be plus 0.00120. And so this is going to be 0.00120. So now we've got a conjugate base. We've got an acid. So we made a buffer solution. So we're going to end up using our old friend, David Hasselhoff. So pH is going to be equal to pKa. And hey, that's nice. I got pKa. I don't have to calculate it from Ka. So pKa plus, of course, the log of the conjugate base over the acid, concentration of the acid. So for us, that's going to be equal to 3.1 plus the log of the conjugate base is 0.00120 over 0.00224. So this is going to be 3.1 plus negative 0.271, let's just say 1. And so that should get you about 2.8 for your pH. don't worry too much about sig figs. Like I said, there's going to be one problem where they check that, and I suspect that'll be true with the AP, with the shortened AP exam you're getting. So that's problems 29 through 31. That finishes out this PowerPoint. We'll go on to the titration one on Monday. Like I said, I'll send out a brief little video showing how to determine which type of neutralization reaction and what you have to do once you get there. Hang in there, guys. I know this sucks. It sucks more for me than it does for you, I think. This is not the career I chose. I'm really missing the classroom. I'm missing interacting with you guys a lot. So anyway, take care, guys. Love you.